Hey everyone, so I'm Rand, I'm the CEO here at Zama. We are a cryptography company working on homomorphic encryption, and we're applying this technology both to smart contracts, but also to artificial intelligence and other kind of computation. So the company has been around since 2020. My co-founder, Pascal Payet, is a cryptographer, one of the early guys in homomorphic encryption. And we now have 60 people in the team, including 35 cryptography researchers. So I think that probably qualifies us as one of the largest cryptography research team pretty much anywhere at the moment, to be honest. But everybody really focused on homomorphic encryption and everything related to it. So today I'd like to talk specifically about how you can have private smart contracts using homomorphic encryption. So the problem with a blockchain is that everything is public currently. Why is it public? Because if you need to agree on some state, well, you need to agree on what has been done pretty much. And so the only way to do that so far was to publicly show what you've done and people can then verify it. The problem, however, is that having things public means that everybody knows what you own. It means that you can be easily put under surveillance. It means that every time you make a transaction, there is potentially someone front running you to extract some additional value from you. So overall, I think we can say that Web3 is not as safe as it could be because it's currently very open. So the technology you can use here is something called homomorphic encryption. So the idea of FHE is that you can basically do encrypted computation on encrypted data. So for example, if I'm a user of some kind of service, I can encrypt my data, send it to the server for processing. It wouldn't see the data because it doesn't have the key to decrypt it, but it can still do processing on it, produce a result which itself is encrypted that it sends back to me and I decrypt it. From my point of view as a user, nothing changes, but from the point of view of the server, they no longer actually see the data. This is, of course, very useful for blockchain, but also for cloud computing in general. And in the context of a blockchain specifically, this means that you can have encrypted transactions, you can have encrypted state updates, you can have encrypted on-chain data. Generally speaking, you can basically have everything running on-chain. You can keep the data on-chain, but offer confidentiality and privacy. So this is very different from how you would think of privacy with ZK, where you need to keep the data and do the computation off-chain if you wanted to offer privacy. With homomorphic encryption, everything actually stays on-chain exactly as it is now, but instead of being publicly visible, it can be hidden if you wanted to. So this is great, of course, because it means people don't have to know how rich you are, people don't have to know what you've been doing, and people don't actually have the capability of front-running you when you're making transactions. But it's also very important for all kinds of new applications where you cannot afford to reveal the data. For example, if you want to start doing things like on-chain KYC, on-chain identity management, well, you have to keep your identity on-chain. But if you keep your identity on-chain, everybody can steal it. So with homomorphic encryption, you could, for example, do homomorphic KYC checks for DeFi and things like that. The second thing is, for example, games. Many games require you to keep things secret. For instance, if you want to play poker, you have to hide the cards until the final reveal. If everybody can see your cards, it's not exactly a very fun game. So poker can be easily done with homomorphic encryption by simply keeping the cards encrypted on-chain until the moment where you want to reveal and have the showdown. And finally, things like blind auctions, also very easy to do in FHE. You can effectively bid on things without people knowing how much you've been bidding. And there are other things which are also possible. For example, confidential token voting for DAO governance. You can actually vote in a proposal without people knowing what you voted for and how much you voted with. As you know, there's a lot of pressure when you hold a lot of tokens to vote a specific way. This will remove a lot of that and make the game a lot more fair. So I say in general, the nice thing here is that it adds this layer of confidentiality to blockchain, which right now is really missing. So how does homomorphic encryption actually work? The idea of homomorphic encryption is that you compute on encrypted data. The way that the data are represented, however, is that you have to add some random noise to the actual data. So imagine you've got 64 bits on your machine. The first, let's say, 10 bits will be the actual data you want to compute on, and the rest will have to be some random noise and plus some extra space between the two. The noise is important for security reasons because this is basically the LWE assumption. The problem with having that, however, is that when you compute on this noisy data, well, not only is the data computed on, the noise is computed on. So if you're adding 2 ciphertext, you're not just adding the bits of data, you're also adding the bits of noise. And eventually, if you do too many of those computation, as you could see here, the noise would overflow on the bits of significant data. And at that point, the result becomes incorrect. If you're lucky, it becomes approximative. If you're unlucky, it's become completely random, effectively. So this is why a lot of people have been trying to do homomorphic encryption without having the noise overflow in the data, something that's called leveled homomorphic encryption. So the idea here is just make sure you have enough noise provisioned so that you never overflow on the bits of message. That's great if you know in advance how deep your computation will be. So if you know the depth of the circuit, then you can plan to have enough noise budget to avoid overflow. However, in the case of a smart contract, you don't know in advance how many times the ciphertext is going to be computed on. For example, if you're making balance transfers in an encrypted ERC20 token, well, there's an infinite number of times where that balance can be updated. You cannot tell in advance how deep the circuit is going to be. It can be infinitely deep. So if you, for example, try to do that, eventually the balance will just be wrong because it'll just add some noise to the actual balance. If you're lucky, that means you're richer. If you're unlucky, that means you're losing money. So the way people have been solving that problem is through something called bootstrapping. So bootstrapping is a special cleanup operation where you can take some noisy ciphertext and you can reduce the noise back to some nominal level while keeping the message intact. The way it works is doing some sort of homomorphic decryption, effectively. So you're trying to remove the noise homomorphically. That's a very powerful technique because it means you can compute forever. However, it's very expensive. So when people say homomorphic encryption is slow, it's not because of the basic operations, it's actually because of bootstrapping. So for example, if you're using CKKS or BGV as the scheme, you can do additions and multiplications very fast, but bootstrapping will take 20 to 30 seconds. The second problem with FHE is that if you're limited to additions and multiplications, like has been the case in most FHE schemes, you can only do linear circuits. If you want to do something like a comparison between values which are encrypted, or if you want to compute an activation function in a neural network, if you want to do anything that isn't linear, you're pretty much stuck. You're having to use some sort of polynomial approximation with your additions and multiplications. While polynomial approximations are theoretically exact, with an infinite, I guess, number of coefficients, in practice in FHE, you can only have 2 or 3 degrees in your polynomial approximation, so you cannot get a good approximation. So if you take, for example, a requirement in a Solidity contract where you want to check if the user has enough money to actually make the transfer, well, if you're not guaranteeing the exactness of that comparison, it means sometimes this check will actually pass even though the user doesn't have the money. And that's obviously not acceptable. In other words, if you're only limited to additions and multiplications, there is no way to guarantee the exactness of the smart contract execution. So the way you solve that problem is using a scheme called TFHE. So TFHE is a new generation homomorphic scheme that we're building at Zama that enables homomorphic additions, multiplications, but also homomorphic table lookups. So the ability to do a homomorphic table lookup is really powerful because it turns out that any univariate function can be represented as a table lookup, right? You can take any integer to integer function and basically pre-compute all the possible values and store that in a lookup table, and then just do a table lookup on that, and you've got your function evaluation. So you can do any kind of complicated univariate functions this way. So now that we can compute univariate functions homomorphically exactly, so without using approximations, we can also reconstruct multivariate circuits using linear combinations of univariate functions. There is like a theorem called the Kolmogorov superposition theorem, and like a related thing called the ridge approximation, which basically prove that. So what it means is that with TFHE, you can effectively compute any circuit, however complicated, however deep, without any kind of approximation. We can guarantee that the result of the FHE computation is exactly what you would get if the data was not encrypted. Not only that, it also turns out that evaluating a lookup table performs a bootstrapping operation for free. So at the same time as you're evaluating your function, you're also cleaning up the ciphertext. And it doesn't actually take 20 seconds in this case, it takes a few tens of milliseconds. So the time it takes to evaluate that table lookup is basically a few tens of milliseconds and not like tens of seconds as would be in other schemes. So TFHE really is the only scheme you can use for something like homomorphic smart contracts. The last thing that's really missing here is performance. So we have a 4x increase in performance every couple of years at the moment, but this will dramatically speed up from 2025 onwards once hardware acceleration for homomorphic encryption becomes available. So there is about 8 or 9 companies right now who are planning to tape out by 2025, which means that we can expect anywhere between 100 and 1,000x speed up for homomorphic encryption in a couple of years. So today you can already do a lot of very interesting stuff, but by 2025, FHE is effectively a done deal. The math works, you can compute anything, there is no approximation, it's super easy to use, you just have to make it faster, and then you can deploy that everywhere from machine learning to databases to artificial intelligence. So let's talk specifically about how we can use that for smart contracts. In the case of a smart contract, what you basically have, so let's take the example here of ERC20 contract. You've got a balance. So the first thing you want to do is you want to hide the balance. So that's what we do here. What we built is an FHE EVM extension. So we built a set of precompiles for the EVM that enables you to have those encrypted integer data types in the EVM directly, in Solidity directly. So as a developer, all you got to do is replace your integers by encrypted integers wherever you want to hide information. So in this case here, I'm just saying that the address is public, but the balance is private. And then you have to write some kind of access control logic to determine who can see those encrypted values. So in the case of a token, we're just saying that a user can see their own balance, but not someone else. And then to make the transfer, you basically just do a homomorphic require. So you're doing a homomorphic comparison and then doing a homomorphic check that this is correct. And then you can do your homomorphic addition and subtraction. So from a developer's perspective, this looks exactly like traditional Solidity code, but now you can indicate which variables in your contract, which states in your contract are supposed to be private and what is meant to be public. So this is really nice, right? Because even the visibility of the encrypted state is just Solidity code. So the access control logic is just, again, Solidity code you're writing. You can decide whatever you want in your contract. It's completely open. There are a few problems, however, with doing that. The first thing is, if you're talking about a smart contract, you're implying that multiple users are interacting together. If multiple users are interacting, and if you want composability between contracts, it basically means that all of the encrypted values have to be encrypted under a single key for the entire network. If there is a single key, who holds the private key for decryption? That's the first problem. The second problem is, how do you make sure that validators aren't trying to decrypt arbitrary ciphertext material as part of their required checks? Because if they have to know at runtime if a condition is right or not to fail the transaction, it means they can actually get a decrypted value. So how do you guarantee that they're actually doing this honestly? And finally, how do we prevent users from just copying some on-chain ciphertext states and writing a contract to decrypt it and passing that as input? So how do we basically guarantee that users can only pass as inputs values that they actually created and not some random stuff from the network? For securing the secret key, what we're using here is threshold FHE. So you basically do all of your usual FHE stuff as you always would, but the decryption of your FHE ciphertext is done through a threshold protocol. So that threshold protocol is running on the validators, which means that you can have something like a 2/3 threshold for decryption. So that's great because it means that nobody has the actual key. People just have a share of the key. So you have to do like a secret sharing protocol between the nodes, and then you do an MPC decryption protocol for the threshold decryption. For the encrypted requires, what you basically do is you get the validator nodes to talk to each other and agree on the state that has to be decrypted before they engage in the threshold decryption. So effectively, what that means is that validators have to do the same computation and then agree on the computation. And once they agree on the ciphertext value, they can then decrypt it, and then they can finalize the block. So this will work great, for example, for Tendermint, because in Tendermint, you choose the transaction to include in a block, and then you finalize the block on the next block by agreeing on the state. This is a perfect sort of setup for something like that. Finally, to guarantee that the user isn't inputting some random ciphertext material to the blockchain, we can use some zero-knowledge proofs for the inputs. So effectively, a user, when submitting a transaction that includes ciphertext encrypted inputs, they have to provide a zero-knowledge proof that they actually know the plain text that's encrypted. So by doing that, it's impossible for someone to pass in a transaction some ciphertext that they took from someone else, because they wouldn't be able to generate the proof that they actually know it. So you see, this whole protocol is basically a combination between homomorphic encryption for the actual smart contract computation, multi-party computation for the threshold decryption, and zero-knowledge proof for the input awareness security. So what's coming next? What we would love to have is provable FHE. Provable FHE meaning that you can prove that the execution of your FHE circuit is done correctly. If you can have that, then you can actually start having the equivalent of like a ZK FHE rollup, which would be really amazing for scalability, as you can imagine. And finally, hardware acceleration, which is going to give us the kind of performance boost that we actually need. So if you guys want, I can actually make you a demo, or I can take question now. What do you prefer?
Hi, I've got a question about the size. Let's say the FHE size is really large, right? So would that be a bottleneck when you send, say, FHE encrypted ciphertext to a smart contract?
That's a very good point. So if you just trivially encrypt some LWE ciphertext with secure parameters, it takes about 5 kilobytes to encrypt 1 byte. So you've got a 5,000x expansion factor. It's okay if you're just sending 1 byte, but if you're going to be sending megabytes of data and in a block, well, you cannot have your block be a terabyte, right? It just or a gigabyte, right? It just wouldn't make sense. So there are multiple ways where you can compress FHE ciphertext. So the first thing you can do is you can pack all of your LWE inputs into an LWE ciphertext. So that would mean that you only have this one-time penalty for however many coefficients you have in your LWE polynomial. So that's one trick. The second thing that you can actually do is you can transcipher to a more compact representation and transcipher back to FHE on the server. So you could have like optimal compression for the transmission of the data, and then deflate it on the server side. However, what that means is that you have to do some extra computation server side, which could or could not be acceptable depending on your objectives. There is another way of doing it, which is what we are implementing. We don't have that yet, but we're doing it as a second step that will be in a few months. We actually found a way to transmit data that would be very easily decompressible and that would have zero expansion versus plain text. So the bottom line is, for blockchain specifically, it's not going to be an issue, and we're going to have block sizes that shouldn't be materially bigger than your plain text block sizes.
All right, cool. Looking forward to that.
This is very new work, by the way. I mean, like it's the funny thing is, we published like a demo of an encrypted of a homomorphic image filtering on Hugging Face, and uploading an encrypted image is like 300 megabytes, and everybody loved the demo, but everybody was like, "Oh my god, like an image is like 300 megabytes now, like that's crazy." And in the 3 months after that, there was like at least 4 solutions for compressing ciphertext that came out. So I think people just needed to see that this was an issue to think about solutions, and those solutions are deceptively simple. It's just nobody had to care about it until now. Any other questions?
Yeah. So basically, what you just mentioned, like the near future work you have is to largely shrink the expansion factor for homomorphic encryption while still maintaining the computing capability for the compressed ciphertext. Is that right?
No, so you wouldn't compute on a compressed ciphertext. You would transmit a compressed ciphertext, and then you would expand it and compute on it and recompress it and send it back. When you're doing the computation, it's expanded, but it doesn't really matter as much, right? Because on the server, you can have, you know, a lot of memory or whatever.
Mm-hmm. Okay, I see. And the compressed cipher.
Sorry, go ahead.
I mean, like the compressed ciphertext, like the what's roughly the expansion factor for the compressed ciphertext?
So it depends if it's a public key encryption. So for blockchain specifically, we have a protocol.
Mm-hmm.
We can guarantee 100% basically compression. So, you know, one byte of plain text is 1 byte of ciphertext, but it's very specific to blockchain. It's not necessarily something you can do on like a cloud setup or something like that. In another setup, there are multiple techniques. For example, your fresh ciphertext, you can just pass the mask without passing the A's, you know, in your LB ciphertext, and you can pass a C to generate those A's instead. So you're removing most of the ciphertext there. Exactly. The expansion factor here is it becomes from 1 byte to 5 kilobytes. It goes from 1 byte to 8 bytes plus the seed.
Mm-hmm.
Very, very small. On the way back, it's more complicated because you cannot, you know, compress it this way. But there was a paper published a couple of weeks ago that showed that you can transcipher from FHE to Paillet, and you can pack a lot of data into a Paillet ciphertext and transmit that and do the Paillet decryption on the client side, which is very clever. Effectively, you're using Paillet to evaluate the decryption circuit for your LBLE ciphertext. It's like super simple when you think about it, right? Like, but it works great, and the compression there is 97%.
Wow, yeah.
So yeah, so that's why I'm saying it's effectively a problem that's being solved multiple ways, and so I think, you know, that's not going to be an issue very long.
Okay, sounds good. Thank you.
Anybody else? Or do you want to see a demo?
Hey, Rand. I guess this has to do with the demo, but I was wondering how like expensive the like FHE precompiles are on for example, like Ethereum.
Well, because these are precompiles, it means that the FHE computation is running outside EVM. Effectively, we're using the precompiles to bind Solidity to our libraries at Zama. So this will run as quickly as you can run on your machine. And the gas cost is whatever you want to set the cost of your precompiles. This is not like an EVM execution.
Okay.
It's running outside the EVM, and it's just being linked to the EVM through the precompiles.
Okay.
So yeah, if you want your network to put like a 0 fee on that, you can do that. I would expect that confidential transactions will be 10x more expensive for now, and that price will go down with accelerators. The main issue, I think, wouldn't be cost, it would be throughput. In order to get like very high throughput, you need acceleration. If you don't have acceleration, you're probably limited to, I would say, some kind of Ethereum-like throughput. So maybe 10 to 20 transactions per second, which, by the way, is already amazing when you think about it, right? Especially considering that we're doing large integer arithmetics here. But down the line, I think, you know, in 2 years, nothing prevents us from having like 1,000 transactions per second in FHE. Also, keep in mind, FHE EVM is very different from ZK EVM. In ZK EVM, you're evaluating the actual virtual machine in a ZK. With FHE, we're not doing that. We're not evaluating the EVM in FHE. We're adding an FHE data type to the EVM. So it's an extra functionality on top of the EVM as opposed to running the EVM in FHE. So you can run your contracts as you would already, but now you have also this optional feature where you can do encrypted computation as well. And this is really what we're showing here.
Got it.
So I can show you how this works. So very simple again, as I explained earlier. So this is an ERC20 contract. my balance is encrypted. Then here I've got, my transfer function, the amount is encrypted. By the way, there is no syntactic sugar. The screen I showed you on my presentation, I have to update it, to be honest, because we thought we could do operator overloading in Solidity, but it turns out you cannot do that. So we have to call it by name, but whatever, it is what it is. And then, here the balance of is, just re-encrypting. Effectively, we're asking the threshold nodes to re-encrypt the on-chain balance from the network key into the user's provided key. So the user provides a public key, and then we re-encrypt under the public key. I've done all of this in Remix, so I'm using the usual tools. I'm compiling using the regular Solidity compiler, so there isn't like a specific compiler we're providing or anything like that. And then I'm using MetaMask to deploy my contracts. So we have like a Zama testnet running internally right now. All right, it's deployed. And then we created some demo applications. So we have one for token transfers and one for blind auctions. So a token transfer, I'm going to paste my contract here. You can see there is no supply. So I'm going to mint a couple of tokens. What happens here is that I encrypt the value 2. I generate the ZK proof. I send the transaction. I just wait for the block to be computed. I'm very rich in Zama tokens, by the way, as you can see, obviously. There we go. Okay, so that's done. And then now I'm gonna check my balance. So you see, if I ask to check my balance, this is basically what's different from a traditional blockchain. Because my balance is encrypted, I have to send a request to the network to decrypt my balance. I approve it by signing it to prove I'm the one making the request. And you can see it's actually saying I have got 2 tokens. And now if I want to make a transfer, I just go to my second account. I'll copy that. I'll make a transfer here, encrypting 1, producing the proof. Great. Oh, that was quick, actually. And then if I look at the transfer on the block explorer, what you can see is that it's a regular EVM transaction, but the data that you would see on chain is just this blob of randomness. So this is what's so nice, is that from the developer's perspective, it looks like writing any standard contract. From the user's perspective, it looks like interacting with any standard, web dApp. But if you look at the data on chain, that's what you would see. And so, as I mentioned, here we just have like a demo for like a token, but you could do the same for blind auctions, for example. So a blind auction is an auction where people don't see the bids of other people. So here the bids would just be encrypted integers. You'd keep like an encrypted integer map of like who's been bidding what. And then you're using an encrypted tokens for your bidding. When a bid comes in, so when you call the bid function, what we basically do is a homomorphic CMUX, which is just effectively a ternary operation, checking that if the value is higher than the highest bid, then set it to this new value, otherwise keep the existing bid. And then once you've done that, when people want to claim, you just check that whoever is making the claim is actually the highest bidder, and then you give them the object, and then you basically consider this to be claimed. So you see, again, this is so much easier than using ZK to do the same thing, where you would have like a bunch of offline stuff, then you have to put the proof on chain, verify the proof. This is like 3 lines of Solidity code, right? It's like super, super, super simple. So performance-wise, we can support arbitrary arithmetic, so we can do up to 256-bit arithmetics. However, doing 256-bit FHE operation is still quite slow. So like it takes like 3 seconds to multiply 2 256-bit integers. We expect that to be 10 times faster in the coming months. So I think most likely for like, I would say at V1, we would hope people will use like 32 or 64-bit integers, not yet like the full 256 bits. And to be honest, they're a rarely seen use case in blockchain where you actually need 256 bits of precision. I mean, you know, like maybe Shiba is like the only token that has like 15 decimal points or something like that. So I think that's fine. And again, you know, this is getting better and better over time. One thing you guys might also be interested in, we are going to be launching a private testnet this summer at ECC. The idea here is to give people access to this internal testnet I'm showing here so that they can start playing with the technology, they can start building contracts, getting a feel for what it looks like to build like private dApps using homomorphic encryption, and then eventually we'll make that public. We're not planning on launching a network. However, we are partnering with an existing chain who's going to be launching one.
I think we have some questions in the room.
I was wondering if I could ask a question about, you mentioned like this like new component of like lookup tables in your FHE circuits earlier. And I don't really know anything about this like entire domain, but like something that sounded kind of like interesting to me was like, so these lookup tables like solved the problem of like arbitrary precision computation. And also you mentioned that it gave like, it also like removed the bottleneck of like the noise reduction step, like of bootstrapping by like 1000x. Like, so it solved two of these in my mind, like core problems that you were dealing with. Is that like just a coincidence that like lookup tables also give you this like free noise reduction step? Or like and also so generally if you could like sketch out like a more precise mental model of like the concept of noise generally, that would be helpful.
Right. So it actually started the other way around. So TFHE originally was only for Boolean gates. So it was a way to compute Boolean gates homomorphically. But the way that it did that was by effectively encoding like a specific vector in the bootstrapping procedure. So like the first step of TFHE was, okay, let me backtrack a little bit. So TFHE was an FHE scheme. And the only thing it could do in the very, very first instance was to compute homomorphic additions. And it could also do very fast bootstrapping. And the way that it did very fast bootstrapping was by effectively what we now know was computing a table lookup on the identity function. But nobody really thought about it as a function back then. You know, people were just like, oh, you know, we basically have to do this kind of blind rotation thing. And to guarantee that the output is the same as the input minus the noise, you know, we have to make sure that we're outputting the same thing. Effectively, that's just the identity function. And then they realized, oh, but wait, hold on. Maybe we can manipulate that and we can do that for Boolean gates. So instead of like computing the identity function, we can compute a Boolean gate on a 1-bit or 2-bit input, right? So they started doing that. And that was kind of like the moment where TFHE became popular because people were like, oh, wow, you know, it's not just additions and multiplications anymore that we can do. It's also Boolean circuits, which was amazing. And then at Zama, we looked at that and we're like, wait, hold on. What if we try to go from like Boolean gates to, you know, integer functions, see what happens. And so that's what we did. We extended effectively the definition of TFHE to support integer ciphertext and integer table lookups.
Concretely, what's the size of table? Like what size tables can you support?
Theoretically, any size.
Yeah.
Pragmatically, it depends on the crypto parameters and the performance that you're willing to incur. Every additional bit of message that you want to evaluate, that's going to double the size of the parameters. So it gets exponential very, very quickly. So in practice, we find that anything more than like, you know, 10 bits is impractical, and even 10 bits is already too slow. So what we do instead, to support very large integers, we use small 4 bits messages, and we then use either like an RNS or a radix representation to compute larger integers. And so by doing that, you know, you can just do whatever you want effectively. So that's how we do it. Like that's the trick. So we don't we don't have a table lookup on 256 bits because that would be insanely, you wouldn't be able to pre-compute it. Rather, what we have are 256-bit operations on integers, which are composed of smaller 4-bit table lookups.
Well, thanks.
I had a quick question as well. You mentioned like the throughput of, I think, like 10 to 20 TPS. Is that with just this like one encrypted variable demo that you were showing? Like that would be about throughput there, or is that like some sort of full smart contract transaction with like many variables?
I mean, how do people measure transaction throughput in blockchain in general? I mean, I think we would use the same kind of benchmark. Most people, when they talk about transaction per second,
what is that benchmark? You said you use the same benchmark?
Well, I'm saying in general, if you're trying to measure throughput of a blockchain, encrypted and unencrypted, you've got the same question, which is what kind of transaction are you talking about? Is it 10,000 token transfers, or is it 10,000 NFT auctions? Obviously, the complexity of the contract will determine the transaction throughput. In general, when people talk about throughput, they're talking about throughput for ERC20 token transfers, because that's like the most common operation that people actually see. But it's not impossible that someone takes the entire block for their one single transaction, right, that they're doing, in which case your throughput is 1 per block in this case. So I think for us, when we say we want 10 to 20 transactions per second, we mean 10 to 20 encrypted token transfers per second.
Got it. Thank you. And then the other question I had was, you showed it in the demo, like this token balance that a user had that was encrypted, and then you made like a request almost through MetaMask to the network, and you like decrypted the ciphertext in the network and then got the token value back. How do you ensure the privacy of that in flight? Like, does the server not have that value just exposed?
No, because what we do is the RPC node would. Right. Well, it depends actually. No, the RPC node wouldn't. No, sorry, not at all. So what happens is you're not just doing a threshold decryption in this case, you're doing a threshold re-encryption. So the threshold network basically converts the ciphertext that's encrypted under the key of the network into a ciphertext encrypted under the key of the user. So when you're transmitting it back, it's encrypted under the key of the user. And so nobody can actually see the value because they don't have the key to decrypt it.
I see. So some decryption happens in the network, and then on the client, the final decryption happens.
Yeah, it's a re-encryption, basically. You can see that threshold network is a re-encryption network in this case.
I think that makes sense. Thank you.
A follow-up on that scenario. So does the user's identity get leaked? Or is it like your own address? Does anybody see your own address?
Yeah, you do. So it doesn't change anything to the way the blockchain works. If you're making a transaction, you're making a transaction, so people know your address, you sign with your wallet, everything is exactly the same. The inputs to your transactions are private. Having said that, if you want to have privacy in terms of token transfers, so if you don't want people to know who is the recipient of your token, it's actually very easy to implement something like Tornado Cash in pure FHE without ZK. Effectively, what you would do is when a user initiates a private transfer, you would encrypt the amount to be transferred. You would also encrypt the address of the recipient, and you would store that in effectively a homomorphic key value store in the contracts, right? So you're basically saying, this is the encrypted address of the recipient, this is the encrypted amount that corresponds, and you just have that like in an encrypted key value store. And whenever someone was to withdraw money, they basically have to call the withdraw function, which will homomorphically check that the address of the caller matches one of the encrypted address in the list of pending transactions, and then transfer the encrypted amount confidentially. So a simple key value store in FHE gives you the same privacy guarantees as Tornado Cash with ZK.
Cool, thanks. And presumably this key value store, homomorphic key value store would be expensive.
Well, I mean, yeah, but at the same time, it's easily parallelizable. So again, we could always, if we think that this is going to be a common thing, we can expose it through a precompile that just effectively does that in parallel on like a big machine or whatever. Like
Okay.
that's not the nice thing about a blockchain, and the reason why we're able to get such good performance versus what people think is doable in FHE is because every operation is done sequentially in a blockchain. And what that means is that we can use 100% of the compute power of the machine run by the validators for every FHE operation. So that's amazing, right? Because if you're running this like on an AWS server with 100 cores, you can literally use 100 cores for all of your FHE operations, which is an amazing way to speed up things. If you were to do all of that sequentially on a single core, it would be much, 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 much longer to compute. So that's why I'm saying like blockchain is a perfect use case for homomorphic encryption because things are happening sequentially. So you can use 100% of the compute power for every FHE operation. Smart contracts are very simple programs compared to something like neural networks. So the size of the computation is also very small. And the users are already used to things being slow and expensive. Perfect, right? So I think like it's an ideal first use case for homomorphic encryption.
Cool. I have another question. Sorry, I probably have too much questions, but so the FHE itself is CPA secure, it's not CCA secure, right? In the sense that if you deploy a FHE on a smart contract, then some malicious user can try to query this FHE and try to see if you can get a correct encryption. And if you try it enough times, it breaks the CPA security. So this is a classical reaction attack that's useful for used in the cloud computing scenario.
Yeah.
Does that apply? I mean, I just want to see how your solution is robust against this kind of attacks.
Well, I mean, I guess that depends on what your contract is exposing as endpoints, right? I think that if your contract is revealing some information to anybody asking, I would argue that this is a problem with the application, not a problem with homomorphic encryption, right? If you're making okay, sure. So the only thing that's being leaked, to be honest, is the require functions, because you need to fail transactions with certain conditions. So that bit would become public eventually. But again, it doesn't really matter because you don't actually get the value. You just get a control bit saying this condition passed or didn't pass. And so potentially, people could write contracts which would use, those required checks to do some arbitrary computation. But why would you use it as a user? I think I would consider that to be a malicious contract, and I would hope people don't use malicious contracts in the first place, regardless of homomorphic encryption. But for FHE specifically, there is no information leakage because the data you're getting back as a user has been decrypted already, right? So like there is really nothing aside from the message itself that you're getting back. Like there is no way for you to retrieve the private key of the network because there is no like noise from the key or anything like that you're actually getting back.
I see. So this re-encryption really stops you from the incrementally increase the noise, try to see where the threshold is.
Exactly. Because like your inputs can be noisy if you wanted to. It just would make the computation fail, which would make the transaction revert. So, actually, no, that's not even true, to be honest. I'm not even talking right. If you're trying to do that, you will get an incorrect result in the computation at some point, and it'll just fail like as if you're trying to pass a random value.
Okay, cool. Thanks.
This is new territory, by the way. We're working on a security proof. A security proof or something like that for a protocol like that combines, FHE, ZK, MPC, a blockchain. Let's just say that I don't think I've seen like a system that complicated in production with cryptography like that yet. That has to be one of the most complicated protocols to ever go into production, to be honest. So lots of works around that. And of course, I think we're not going to be launching a mainnet this year. We're going to launch test nets. We're going to publish our white paper in the coming months. And we're hoping people will find attacks so that we can fix them before things go into production. I'm sure there's going to be some stuff that we missed, that someone is going to figure out. And that's why we make everything open. That's the whole point, attack it. And if nobody can break it, then, we feel a little bit more confident. Any other question, guys?
Yeah, so like I have a question about maybe some parameters, since we are working on hardware acceleration. And yeah, if I recall correctly, like the RNS like you use for this like homomorphic encryption is like around 64 bits, right? And the only bottleneck, maybe only bottleneck operation in homomorphic encryption is the NTT.
Right, the NTT or the FFT, yeah, exactly. So the bootstrapping operation that we use effectively just does a bunch of NTTs or FFTs, depending on what you want to do. The NTT for FHE is about 4 times slower than the FFT. So that's why we use the FFT whenever we can use the FFT. It's just faster on the CPU. On an accelerator, probably will be an NTT version. If you can get like anything above 100x speed up, then that's a game changer. You're going from a few hundred milliseconds to a few milliseconds of compute time for large integers. And if you can do that, I would argue, blockchain is a done deal, pretty much, right? So today, we've got like a good enough performance with CPUs for blockchain to make it practical. With acceleration, it'll make it cheap, and it'll make it like, very high throughput.
Right. Yeah. So like we can basically do 256 bits, and NTT, like the size of the NTT is like 2 to the 26 in around 26 milliseconds. So that's a number we have right now.
Yeah. I mean, and we don't even need entities that big.
I understand
that. So yeah, no, I mean that's great. Like I'm my job is to build everything that people can use with those accelerators when they become available. That's it, right? Like I'm the tooling provider, if you want. I'm the cryptography provider. We don't do any hardware stuff, right? I think, we have a small team working on that, but honestly, I think, your team, Leo, and the other people working on that, you're going to do a much, much better job than we can ever do in hardware.
Okay, yeah.
Maybe something you guys might be interested in is we think that it's possible to do rollups with FHE as well. So ideally, ZK rollups, as soon as we have like verifiable FHE, I think that's probably going to take another couple of years before it's practical for real. However, we can already probably do optimistic rollups with FHE because optimistic rollups, well, they don't require the ZK computation on top. There are just a few things to figure out in terms of like the verification when there is a dispute. But at least, the nice thing is if the blocks are not bigger, then potentially we can make it fit even on Ethereum's rollup. So it's possible that you could build like an FHE rollup even before we have verifiability. I'm more on the ZK rollup kind of camp, to be honest, but whatever, like at the end of the day, what matters is that people can use it.
So the reason it's like, is that people checking the validity of this rollup would have to like execute the FHE computations themselves. And like, in order to do that on ZK, you need to basically snarkify the operations you're doing in FHE.
You need to snarkify your FHE operations. And so like, think about the multiplicative effect here, right? Like you're trying to do a ZK circuit of an FHE circuit.
Yeah. It's already,
right? But we'll get there. I think we'll get there because we have some promising avenues of research. That's why I'm saying I think in a couple of years, it'll be doable. And when I mean doable, I mean that it takes less time to verify than to recompute the whole thing. Because if it takes you just as long to verify than it takes you to redo the FHE computation, just redo the FHE computation. And so I think, that's a couple of years away.
Cool. Great. Any more questions from anyone? All right, thanks so much for your time. That was this is an awesome.
Pleasure, guys.
Work.
Anything else, just, hit me up on Twitter if you want. I'm just going to put my address here. Very easy. And I'm going to put my email as well. I use Telegram, but to be honest, it's just so full of spam. My Telegram right now, like I don't see all the messages. Twitter, I think, is cleaner for now.
Cool. Great. I'll share that with the group as well.
Awesome.
All right.
Great. Thank you for having me, and speak soon.
All right. Bye, everyone. Thanks.
Bye.
Thank you.